An Introduction to Set Theory and to Philosophy and Methodology of Mathematics and Computer Programming by Jan Plaza.
An overview, axiom of pair. We are going to present a theory of sets called ZFC. Any theory is based on axioms. Axioms are statements which are assumed without a proof. Axioms fall into two categories. There are logical axioms and specific axioms. So first about logical axioms. Logical axioms are axioms of logic, formulas which are valid and on which classical logic is based. One of such axioms is the law of excluded middle, A or not A. Axioms of logic involve also axioms of equality, and I'm not going to formulate them here, but I would like to mention that one of the consequences of the axioms of equality is the following. If x is equal to y, then whatever we say about x holds exactly when it holds when we say it about y. The notation I'm using here is as follows. A formula A involves three variables, a free variable v. This variable is here replaced in all its occurrences by x, and in this case the variable v, or more exactly its three occurrences, are replaced by y. If x is equal to y, then whatever the formula A says about x, it says exactly the same thing about y. And the entire formula is of course universally quantified. Now, specific axioms, in the case of ZFC, involve so-called axiom of pair, which is as follows. For all x1 and x2, there exists a set capital Y which contains exactly xy and x2. This will be written as follows. For every little y, y is a member of capital Y if and only if y equals x1 or y equals x2. So please notice that this part of the formula says that y, little y, is a member of capital Y exactly when y equals to x1 or y equals to x2. The set capital Y consists exactly of x1 and x2. Whatever x1 and x2 we choose, there exists a set Y with such elements. Let us formulate a simple corollary to the axiom of pair. For every x, there exists a y such that for every little y, y is a member of capital Y if and only if y equals to x. So for every x, there exists a set which contains exactly x, contains x and nothing else. Proof. Again, for every x, there exists y such that for every little y, y is a member of capital Y if and only if y equals to x or y equals to x. Now, of course, this disjunction is equivalent to just y equals to x. So we obtain the formula as required in our fact. Let's think about some consequences of the axiom of pair. Let us recall that we previously proved that even without any specific axioms, the theory implies that there exists a set. That set that is known to exist, I'm going to denote it by x0. And given that x0 is a set, the fact we proved allows me to formulate a set x1 that contains exactly x0. Now, given x1, I can form a set x2 that contains exactly x1, and so on. Also, more complex sets can be formed choosing two of the sets whose existence has been established and using the axiom of pair. Now, when we think about these sets, there are two important questions that cross our mind, and questions which need to be answered by the theory. Are such sets all different? And thinking specifically about x1, is the set that contains exactly x0 unique? Who knows? Maybe there are two sets which are different, and each of them contains exactly x1, x0. The answer actually will be no, but we need to make sure that the theory answers the question.